Matt. We make up the green team with Mark and Michael also. Today we're going to go to the overview of the steady state, the step response analysis, the sign and relay analysis. The PowerPoint is going to consist with an overview of the system, SSOC analysis, step response, the analysis for the FOPDT, the modeling, as well as analysis, sign and relay analysis, and then a conclusion. This is the basic block diagram for our system. Our manipulated variable input is the motor power. It goes through the system and comes out as the controlled variable, as the drive speed and RPMs of the engine. Here we have a schematic of our system. We have a speed transmitter that measures the speed of the engine. It's recorded by the controller, the recording controller, and then the speed controller adjusts the speed accordingly. Knowing the speed here and the gear ratio of the gearbox, we can determine the speed of the actual mixer. This is a constant input response. The blue shows the transient stage and the red is the steady state. This is for an input of 5%, and we got an average RPM of 75 with about plus or minus 12 RPM. We did this in 5% intervals to create the SSOC for our data. From 0 to 100%, all the ranges are linear. This is a step response of our data. We start out with a percentage input, let it reach a steady state period, and then step it up in increments of 20%. Using this, we find a DM, which is the difference in our input, and a DC of our output. And we have a DC over DM, which gives us our gain of about 17.4 RPM per percent. Also, from the step response graph, we can find the dead time, T0, and our time constant, tau. We do this by finding the T0 is the difference in where the input starts and where the actual output starts to increase. And the tau is 63.2% of the DM, and at this point where it crosses the output range is the time constant. This is the tau, this distance here. Here's the same graph. This is for the step down with the same DM and the same DC, which corresponding to the same gain of 17.4 RPM per percent. The same type of analysis can be conducted on the step down to give a T0 and a tau, and for the 25% to 5% step down was the same as the step up. This bar graph here shows all the step up and step down for all the ranges. For the gain K, it's pretty consistent all the way across the board. Have a little hiccup there. I'm not really sure why that one is a little lower, but all the other data is pretty consistent with the K. Our dead time T0 is such a small number and hard to measure, and after significant figures were factored in, they all came out to be about 0.1 seconds for all the ranges. The time constant tau, it varied through the data points, pretty consistent in the middle, but at the beginning and end there's some points that were a little higher than others. This just shows the theory behind the step response and the model. To get the model, we can adjust the parameters in here to fit it with actual experimental data and to get the parameters for the model. This is a step up. The red shows our actual experimental output, with the black indicating the model. And we adjusted the model to fit the output the best we could, and these are the parameters we came up with. The gain K was the same of 17.4. The T0 and tau were also pretty close to what they were with the experimental data. Here's the same concept with the step down. We fit it, and as with the step up, it fit pretty closely, and the numbers are pretty much the same. This is just showing a table of the parameters that were used in the model equation to output the model graph. Here's a bar chart. It shows the up experimental, the up model, the down experimental, and the down model. For the most part in the middle, it was very consistent. In the lower and upper ranges, we had some slight variation in the gain K, but not too much. Here's the same type of chart for the dead time. With our system, as with the K, all of our points are pretty close for the experimental and the model. The time constant, it's the one that gave us the most variance in the data. But as far as the model up and down, they were pretty close to the same, as well as the experiment up and the experiment down. Here, this shows a block diagram with a sine response transfer function, and this is the basis for the sine analysis. Here we have an example of a sine input for our experiment. The green indicates the input of the system, and the blue is the output. And from this graph, we're able to get the amplitude ratio and the phase angle. We varied the frequencies in the sine response, and we're able to come up with a Bode plot. In the Bode plot, we get the K by the asymptote here, which was about 17.6 RPM per percent. The tau, we got at 0.7 seconds, which we get this from the amplitude ratio equation, and we analyze it at the frequency at point A here. T0 comes from the phase angle equation, and we use it at a frequency of the ultimate, at the ultimate frequency, which we found the ultimate frequency at minus 180 degrees and the corresponding frequency, which was about 3.2 hertz. Also from this, we come up to the amplitude ratio, and its corresponding amplitude ratio, 1 over this, gives us the ultimate controller gain of about 0.4% per RPM. The slope at the higher frequencies of the amplitude ratio, the negative of this slope gives us the order of our system, and for this it was about 2. Here's the theory for the equations for the sine response. As with the step response, we can vary these equations and try to get a model to fit. This is our model of our Bode plot for the sine response. For this, we change the parameters to make it fit the experimental data. For K, we want it to fit these top points here, and we got about 17.4 RPM per percent. For tau, we tried to make the model fit as closely in the corner. We got 0.2 seconds. And for T0, wanted it to match about negative 180 on the phase angle, and we got 0.1 seconds for tau. Here is a comparison bar graph of the K, the gain for the experimental and the model As you can tell, they're very close with a slight difference. Here's one for the dead time in seconds. We had quite a bit of variation in the lower range and some in the upper range. It's really not as bad as it looks, but the scale of the chart makes it look a lot more varied. As for the time constants, they're pretty consistent as well, with little variation in either of the ranges. The ultimate frequency that we got from the experimental model was pretty consistent for the lower range as well as the upper range. The controller gain, however, varied a little bit more. And then now Matt will tell you about the relay response.